this. That's important. Okay. First off, my apologies. Yes, I was just bragging about how, oh, I don't get sick, blah, blah, blah. Thursday night, I still wasn't feeling well. Like, oh, whatever, I can't do this. I can't. So I, in the past, if I'm not, just not well enough to go to school, then I would have just hosted online, but I was truly very ill, and it wouldn't have been very fun at all for anyone, especially me. And that's important to me. So what I did was I posted just some review questions to work through along with the solutions. So just some practice. Now that's from chapter 6 and 7. Okay. And oh yeah, the solutions follow. I meant to delete that first page. Sorry. One thing that I do want to point out is I caught my own error, if you can believe that. Well, actually, we can, Emily. I know. Okay. So on what was this, October 20th or something? I lost the date there. But at the very bottom, when we find the transitive closure, I said, oh, you try it on your own. And then I'll post it in the notes when I post them. So I went downstairs to my office and I thought, there, now I've done it. But I forgot something. Oh my gosh. Where is it? Oh, of course it's at the bottom. Haha. So I posted an update. I said, here's the transitive closure. Here are all the things that are missing for it to be transitive. Transitive meaning if I can get from A to B and B to C, then I also need a path from A to C, right? And that can be as long as I need it to be. And so hopefully I didn't miss any, I said, because we're avoiding the matrix multiplication like the plague. And so we're just going by I guess. And so I did. Because what's a route that I could take? I could go from 4 to 1 to 3 back to 4, which means I should have a self loop, right? Or a reflexive loop on 4. And I should have had one on 1, 3, and 4. Okay. So that might help when you're doing those practice problems. It wasn't until I was doing those, I was like, wait, I don't think I did that. Sure enough, caught it. Okay. Now, to prepare for this week, I had you read chapter 8 initially, and then I was reading chapter 8. I was like, surely we're not doing all of chapter 8. This is insane. It's very high level stuff. And so then I went back to the course outline and I saw, oh, phew, we're only doing 8.1 to 8.3. But then I'm narrowing it down to 8.1, and that's fine. I talked to Steve, who teaches the second course a lot, of the follow-up course to this. Pardon? 121. Well, it's computer science 221 or math 251. They're cross-listed, so they're the same. But anyways, he says, oh, well, that's actually harder than what we do in 251. So maybe you don't have to do that. So we're not. We're gonna do a nice intro, which is what we're supposed to do. And so what I want to do today is just focus on 8.1 and really get a good handle on 8.1. And I think that we'll feel good about that. It changes for For Friday, oh, sorry. Where is it? Oh, I already changed it. That's why. Throwing myself off. For Friday, we're going to start chapter 9, which is graphs, which is a deal in the course. And so it'll be nice to have a little bit more time in graphs and trees because they're important. Okay. And so we'll do 8.1 today and then move on to graphs and trees on Friday. Okay. Will my voice hang in there or no? We'll see. Time will tell. So here we're only doing 8.1. I'll throw a smiley face in there. I'm happy about it. Feels manageable. Okay. But also that means note we're starting chapter 9 on Friday instead of next week. Okay. So since we're only doing the one section, I had to stop myself from highlighting the whole section. That felt kind of stupid. And so, but we'll go through it in quite some detail. Okay, so recursion is something that you're going to see in computer science, but I think you don't see it until term 2. Is that true? Not in term 1. Okay, so term 2. So if you're in term 1, then it's too soon. You can just listen.
I know I've heard of recursion, but in computer science, but I don't know when it's introduced, right? I think it's either beginning of next semester or second.
Yeah, so that's why it makes no sense for us to go super deep into it if you haven't seen it in action or anything like that. So, but when we think about recursion, what's happening is, in a way, we're kind of peeling back the onion, right? And to something that's super, super basic, or the basis form, and then we can kind of bloom out the onion, or peel back the onion, depending on which way you want to go. And so one's recursively and one is iteratively. And I guess peeling back the onion would be recursion, and putting the onion back together is iteratively. But you can only confirm that if you know what I'm talking about. We haven't introduced it yet, so that's unfair. Okay. So we've seen the binomial coefficient. And did I start? Sorry, panicky moment. Yeah, okay. Just check. Phew. And I'm sharing. Today of all days would be when it all goes awry. I know that. So the binomial coefficient from before is when we have something like n choose k, right? How many ways can I choose k items out of n? Okay, and we said, well, one of the definitions for n choose k was n factorial over k factorial times n minus k factorial. That's one option. So we know how to find this thing, and that's a good place to start. It's nice when we know that we can check our answer at least when we're introducing something new. Okay? And so a recursive definition of the binomial coefficient, assuming that n is greater than or equal to 0, you have to have things to choose from, of course, and you can only choose fewer items than what you have. So these are all kind of gimme assumptions. Okay. Then we define n choose k by And here we say n choose 0 is 1. That's what we're going to call our basis. Okay. And just as a side note, n choose n is also 1. So if you have something that looks like n choose n, then you can rewrite it as 1. But usually what we're going to end up doing is we're going to have n choose 0, right, as our goal. And we're going to rewrite our choose functions until they're all just a bunch of n choose 0s. Okay? Because n choose k defined recursively is n minus 1 choose k plus n minus 1 choose k minus 1. Okay? So here, right, what we can do is we can rewrite n choose k, right, and we can peel it back by replacing n choose k with these two choose functions, which are slowly but surely going to get smaller and smaller and smaller. Yeah. Okay. So we've got 5 choose 2 there. How about, I'm lacking creativity. Should I do 4 choose 3? Only because I don't want to create a terrible amount of work for myself or you. So there is an example here for 5 choose 2, but what we're going to do is we're going to add a page here. And I need some lines. Dink. Okay. So as an example, calculate, what did I land on? 4 choose 3? It's still quite a bit of work. Oh well. 4 choose 3 by using the recursion, or by using recursion. I should say the recursive definition, but which is n choose k can be rewritten as n minus 1 choose k plus n minus 1 choose k minus 1. Pretty sure. Just going by memory here. Yeah. Okay. So nothing to it but to do it, right? All right, so n is 4, k is 3, and using a lot of brackets, here we go. 4 choose 3 is 4 minus 1, which is 3 choose 3. Oh, that's nice. Why? It's one of those basis ones, right? N choose n is 1. Wow, maybe I picked a good one after all. That's good. Okay. I'll stop congratulating myself. 3 choose 2. This is 1. Okay, maybe it does come into play as a basis more than I let on. That's what I get for winging it. So these kind of basis definitions where I can replace a choose function with just the 1 or some value, then it's called a basis definition, I guess. Okay. So this I can replace with 1. We're not so lucky with the 3 choose 2, right? So now, what am I going to do? I'm going to do another, I'm tempted to say iteration, but it's another recursion, right? Because I'm going backwards, I'm making it smaller. So then I get 1 plus, and I'll put kind of big brackets because the 3 choose 2 is going to be replaced by 2 choose functions, right? So, and I want to keep those together. So 3 choose 2 makes 3 minus 1, 2, choose 2, okay, plus 2, choose 1. Hey, another basis. Nice. Okay. We're not done. 2 choose 1. We have to break it down so that it's either 2 choose 0 or something choose 0 or something choose itself. 1 plus 1 plus, and again, I'm going to go crazy with the brackets. 2 minus 1 is 1, choose 1, plus 1, choose 0, which is another basis. So the only one I have to work on is the 1, choose 1. Okay. 1 plus 1 plus bracket, bracket. No. Oh, ha, what did I miss? 1 choose 1 is 1, and choose n is 1. And also we can't choose from 0. Phew. Exponentially is a good question. I would say generally yes, but I don't know by what power. But it does, there is in the exercises, I think it's the exercises, there's one that we're gonna do that's quite hefty. Or maybe I should read it or leave it as an exercise to the reader. I always hate coming across those. Just means they're too lazy to do it. Okay, 1 plus 1 plus 1 plus 1. That I can handle. Yeah.
I was gonna say, I didn't see the 3 over 2. Like, how'd you form that from 2 to 2 plus 2 to 1?
Oh, okay. So this 3 choose 2.
Yeah.
Okay, so we're trying to calculate 4 choose 3, but n choose k. I can break it up as n minus 1 choose k plus n minus 1 choose k minus 1. So if k is 4, or sorry, if n is 4, then n minus 1 is 3. K is 3 plus n minus 1 is still 3, but k minus 1 is 2.
Yeah.
And this is all coming from that choose function, which is this. So we could do it with the factorials or the, I think it's NCR on your calculator. NCR on your calculator. And choose R. Just a matter of notation, R instead of K. So we can do it on our calculator, but what's your calculator doing? This. I know, womp womp. Breaking it down until it's just 1 plus 1 plus 1 plus 1. Okay. So, yeah, we're here. 1 plus 1 plus 1 plus 1. Bet you didn't think you'd see that today. I count 4. Yeah.
So do you just use like the 2 rules where it's like n over what n choose n is equal to 1 and n choose 0 is equal to 1 to break the equation down to just 1s?
Yes. Yeah, you keep going until you arrive at something that you can replace with just the ones, so those two that we defined earlier. So you have to keep going until there's nothing but ones left. And sometimes that can take a very long time. But on the plus side, we can confirm 4 choose 3 on our calculator. 4 choose 3 on our calculator is 4. Whee! So that's fun. What's another way that we could confirm n or 4 choose 4? 4 choose, oh, I've been saying 4 choose 4, sorry. 4 choose 3. Should just call in sick all week. 4 factorial over 3 factorial over 4 minus 3 factorial. I'm going to simplify the 4 minus 3 to see if I get anything good. 3 factorial times 1 factorial. Now, remember the trick to simplify this? 4 factorial is 4 times 3 factorial. I go until I reach the highest value in the denominator, and then I can cancel them. So then I get 4 times 3 factorial, because 4 factorial is 4 times 3 times 2 times 1, right? That's recursive, sort of. And so, oops, not equal to, divided by 3 factorial. 1 factorial is just 1, right? Because 0 factorial is 1 by definition. So 1 times 0 factorial is 1 times 1, which is 1. So now 3 factorial cancels with the 3 factorial, and all of a sudden I'm rid of those factorials, and I just have 4 over 1, which is 4. Which is exactly what we found again. So lots of ways that you can calculate it, but I am pretty sure that your calculator would have to do it this way. Pretty sure, where it breaks it down to ones and then adds them up. Because the factorial is a function that you'd have to program. Anyways, I'm not 100% sure, but I feel like it would use this way. Okay. Nice. So here's another example if you're keen. 5 choose 2 if we want to calculate it recursively. 5 choose 2 breaks down into 4 choose 2, right? N minus 1 choose k plus n minus 1 choose k minus 1. But then the 4 choose 2 is not a basis function, so then that gets replaced with 3 choose 2 plus 3 choose 1, and then 4 choose 1 is replaced with 3 choose 1 plus 3 choose 0, so it gets out of hand pretty quickly. Turns out I picked a really good one. All right, those match up. So now I'm peeling back the onion, going through them. I get a 3 choose 0, so that's nice. That's where I get the 1 from. They've gone kind of snazzy and combined these. 2 times 3 choose 1, that's fine. Then you only need to do 3 choose 1, break that up once instead of twice. I probably would have just left them as they are, created a little bit more work for myself, but not a terrible amount. And so eventually, right, once you kind of peel these back, then you're left with multiplication and addition of ones and some numbers, some multiples. Yeah. Okay. Good. Any questions about that? Oh, so it would just be one plus one plus one plus one, whatever. But because they got all fancy and said, well, I have 3 choose 1 plus 3 choose 1, I can rewrite it as 2 times 3 choose 1. And then I have the 2 multiplier out front here on 3 choose 1. Let's see, where's the color I haven't used? Orange. Orangey glad. All right, like that. And then that's where you get the multiple from. And then here again, we have 2 choose 1 plus 2 times 2 choose 1. So they've combined it to 3 times 2 choose 1, and then dealt with the 2 choose 1 and broke it up. And then we're all good. Yeah. A little bit sneaky, but like I said, I probably wouldn't do that just because I just like monotony. I like to do tedious things because it makes me feel like I'm really good at it. That's true. Yeah, don't do it in your head. Oh no. Oh no. So definitely a write it down and be super careful every step type of situation. Yeah. Okay, so we'll come back to an example of that in the exercises. I think it's in the exercises somewhere along the way. All right. So another thing that we can apply this to is evaluating polynomials. And so just to talk about polynomials for a moment, polynomial is something that looks like a subscript n, which is just the coefficient on x to the power of n. So here I have an nth degree polynomial because the highest power is n. Okay? And then each power is less than n, right? Decreasing all the way down to x to the power of 0, which is 1, which has a coefficient of a subscript 0, which means that we don't usually write it. So here, I'll just make a note. So a polynomial looks like this: a subscript n, x to the power of n, plus a subscript n minus 1 times x to the n minus 1, plus all the way down to a2, x to the 2, plus a1 x to the 1, plus a0 x to the power of 0. That doesn't look like an a, I'll fix that. Okay. But in this definition, they're leveraging 2 things, right? X to the power of 1 is just x, right? And so here, and also x to the power of 0, anything to the power of 0 is just 1. So then I have a0 times 1, but I don't need to write that. X to the 0 is 1. And so that's how they got to this kind of a little bit cleaner form. Yeah. Now, for example, something like 3x to the 4 plus 2x to the 2 plus x minus 1 is a polynomial degree 4. Degree 4 because I've listed these in decreasing powers of x, and so 4 is the highest power, and so that's the degree of my polynomial. What's another thing that we notice? I go from x to the 4 to x to the 2, which means what? The coefficient on x to the 3 must be 0. So I could rewrite this as 3x to the 4, and then I'll do plus 0x to the 3 plus 2x squared plus x minus 1. Just to fill the whole polynomial up. 0 times x to the 3, of course, it goes away, and that's why it's not shown, but technically it has a coefficient of 0. Okay. This got a little weird in the order. You had to be here, I guess. How about I do an arrow? Arrow. There. And then go back up. It's sort of recursive. Do this and then go back. All over the map. Okay. If you had to evaluate a function like this, 4n to the 3, so a third degree polynomial, plus 2n squared minus 8n plus 9, if you had to evaluate it at n equals 7, probably what you would do, right, because you got a calculator, why not, is just plug in n equals 7 and evaluate, right? And so what we want to do here is we want to count how many addition or multiplication acts that I need to do. Okay? And so why is that important? For speed, right? For computing speed, you want to cut down on the number of calculations that you have to do, right? Or that you make the computer do. So looking at it like this, okay, I've got 4 times 7 to the 3. Now 7 to the 3 is really 7 times 7 times 7, right? So already that's 2 multiplications. And one thing that I'll mention here is notice that 7 squared is 7 times 7, right? So that's 1 multiplication. And what's 7 to the 3? We could define it recursively, right? By 7 times 7 squared. 7 times 7 squared, which I can replace with 7 times 7. That looks like a subtraction. That's not what I meant. So I could save a little bit of time, right, by first finding this multiplying. So multiply and then multiply that by 7 again to get 7 to the 3 and 7 to the 2. Right? So already I've done 2 multiplications and I haven't really even started, right? So here I have 2 multiplications, 1 multiplication, I'll do plus 1 multiplication. Then I can plug in those values. 343 is 7 to the 3, 49. Now back on track. Got another multiplication, 4 times 343. So plus 1 multiplication. I'm ignoring the addition for now, plus 1 multiplication plus 1 multiplication. So far I've multiplied 5 times. And I hope, yeah, which equals 5 multiplications. Once I've done those multiplications, I'm still gonna have to do 1, 2, 3 additions. Subtraction is just a special case of addition, right? And so generally we just say addition. Okay. And so then we have 1, 2, 3 additions. Okay. No problem with that, except there's a sort of faster way to do it. You just have to telescope it first. And so let's see here. What we can do, and where does it introduce it? What we can do is we can rewrite this f of n, 4n to the 3 plus 2n squared minus 8n plus 9 in this telescoping way. Okay, so we want to spend a little bit of time talking about how can we create this telescoping form. When we use this telescoping form, what's happened? All of a sudden, I'm reducing the number of multiplications and additions. 1 multiplication, 1 addition, another multiplication, another addition, 2 and 2, another multiplication, and another addition. So 3 and 3, right? And so that's fewer than before, right? We were doing 5 and 3, right? So now we're down to 3 and 3. So that's good. So that's the reason. But for us, I'm just going to ask you, can you write this in telescoping form? So here we go. Let's work on this one because it's available to us. And why not? Right. 4n to the 3 plus 2n squared minus 8n plus 9 in telescoping form. Okay. For these, I start at the back of the bus. And what can I do? What's the most natural thing that I can do is I can just put brackets, right? So I can seclude this plus 9 and I can kind of imagine brackets. I often write out the brackets because it helps me see it, right? And so this I'm going to write out as 4n to the 3 plus 2n squared plus 8n bracket plus 9. Oops, no bracket. Now I see it, right? I can extract a common n, but it's going to the back of the bus, which is a little bit backwards for me. Of course, multiplication can happen in either order, but it's just going to be a little bit cleaner if you just write the n on the right-hand side, just a little bit backwards. Okay. So now I'm going to rewrite this as 4n squared, right? Because I'm taking out an n from each term. And so I get 4n squared plus 2n plus 8 times n plus 9. Okay. Now I can do this again, right? I can put brackets around 4n squared plus 2n, as well as pull out a common n, and I get 4n plus 2 times n plus 8 times n plus 9. You're peeling back the onion until there's nothing left. Hopefully this is what they had up above. Let me just grab it. It is. I don't need to grab it. There's nothing left to extract, right? There's a common multiple of 2, but I'm just going to leave it in there because they did. And also I only want to have multiples of n because it kind of looks cleaner. Okay. One thing that I will say is that you always want to make sure that you include all of the terms, right? From your leading coefficient down to n to the power of 0, right? And so here, if a coefficient is 0, first rewrite the polynomial including the 0. Oops. Oh, I keep trying to combine the 0 into one word. The 0 coefficient. Maybe we'll do that now. Yeah, maybe we will. In the exercises. But that means I should have done this one first. Eek. I'll parking lot it for a little bit. I put it off because it was going to be so long. This one's fine. So if we have p of x is x to the 5 plus 3x to the 4 minus 15x to the 3 plus x minus 10, and we want to write that in telescoping form, then one of the first things that I'm going to look for is, okay, I've got x to the 5, x to the 4, x to the 3. I'm missing x to the 2. So I'm going to rewrite this polynomial, including the x to the 2 plus x minus 10. So here we go. Rewrite including 0 times x squared. So then I have p of x is x to the 5 plus 3x to the 4 minus 15x to the 3 plus 0x squared plus x minus 10. Now I have all my decreasing powers of x. There's someone by the door, but they don't look like they want to come in. Just hanging out. Confusing. All right. So starting at the back of the bus, I am going to put brackets around all the x terms so that I can see it and get started here. If you wanted to, you could be pulling out a common x right away, right? But just to warm up, I don't do that. But I'm slow. Minus 15x to the 3 plus 0x squared plus x bracket minus 10. Or if you wanted to, you could have skipped to this next part. As long as you're extracting an x from each of the terms, right? So now you have x to the 4 plus 3x to the 3 minus 15x squared plus 0x plus 1 times x minus 10. Then you move on to the next lump of x's, right? And if you wanted to, you could just imagine putting brackets around it, and then in the next step, right away, pull out a common x, so x to the 3 plus 3x squared minus 15x plus 0 times x plus 1 times x minus 10. Okay. Again, imagine brackets around whatever terms have x's left in them, and I get a lot of brackets, but that's good. X squared plus 3x minus 15 times x plus 0 times x plus 1 times x minus 10. And then finally, around x squared plus 3x. So I get bracket, 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 x plus 3 times x minus 15, bracket, x plus 0, bracket, x plus 1, bracket, x minus 10. And that's it. So there you have it in telescoping form, which is, well, that's where I said arguably quicker to calculate, right? Quicker if this is where you're starting from, not quicker if you have to generate the telescoping form and then use it to evaluate. So choose your poison, I guess. Let me add a page here. So that was part A. We wrote P of X in telescoping form. Now I want to use a calculator. That's great. Whoops. Copy. To compute P of 3 using the original form of P of X. So let's grab P of X here. P of 3 is 3 to the power of 5 plus 3 times 3 to the power of 4 minus 15 times 3 to the power of 3 plus 3 minus 10. Now using our calculator, won't be that bad, just order of operations. 3 to the power of 5, I'm just going to break it down a little bit. 243 plus 3 to the power of 4 times 3 is 243. That makes sense. Just hesitated for a bit. Why? Because same base here, right? 1 plus 4 is 5. Phew, they're supposed to be the same. I just had a little blinky moment. 27 times 15 puts me at minus 405 plus 3 minus 10. I have this feeling that we were supposed to keep track of how many calculations we've done. I'll go back and count them. If it asks for that, I can't remember. I think it did. I didn't read that far. Minus 405 plus 3 minus 10, 74. Oh, dang. Compare your speed in parts B and C. Maybe we can just think about our speed in general, not computing speed, multiplications and additions. Now let's do this one. From the telescoping form, which was this, which I'm just going to grab here. P of x is this, so P of 3 is bracket, 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 bracket. 3 plus 3 times 3 minus 15 times 3 plus 0 times 3 plus 1 times 3 minus 10. Starting inside the very core of the brackets, right? Order of operations says that brackets first, but there's a lot of brackets to deal with. So we have to do 3 plus 3. Think about the number of operations, although I'll have to go back and do it again, I guess. Painfully, let's do this. I might regret this. What am I doing? Using one line per calculation so that I can count them. Oh. So I did addition, then multiplication, six times 3 is still 18, phew, minus 15 times 3 plus 0 times 3 plus 1 is 10. 18 minus 15 puts me at 3. 3 times 3 plus 0 times 3 plus 1 times 3 minus 10. 3 times 3, 9 plus 0 times 3 plus 1 times 3 minus 10. Okay. 9 times 3 is 27. Plus 1 times 3 minus 10. We're doing it. We're really doing it. Hey, where'd that 1 come from? Trying to muck it up. No. Sorry. It's from here. There. This 3 is this 3. Let me just convince myself. Okay, phew. 9 times 3, 27. Good. Still, okay, still got it. 27 plus 1 is 28 times 3 minus, okay. $28 times 3 is 84 minus 10 back to 74. This is supposed to be the quicker one, but how many lines did this take? A lot. But that's only because I didn't write out every individual multiplication and addition as a line in the previous one, which I should have done. Maybe I'll leave that as an exercise to the reader. Huh? 1, 2, 3, 4, 5, 6, 7. 7 versus, huh? Well, you can, but so you can do it all in you can do multiple things in one line, but it still counts as 2 things. Were you able to do it faster? Or did you just do multiple things in one line? Oh yeah, of course. Isn't that tempting? Now imagine writing this out in where the lines represent the action. Where would you start? I'd probably start here with 3 to the 3. And I would rewrite this 3 to the 3. 3 to the power of 3 is 3 times 3 to the power of 2. But 3 to the power of 2. So 3 to the 3 is already 2 multiplications. And I would get 2 lines, right? Just that. But then 3 to the power of 4, once you have it, once you have this value, right? That was 2 multiplications in, then you have 3 times 3 to the 3. So now you're 3 multiplications in. 3 to the 5, you can get by 3 times 3 to the 4. That's only 4 multiplications in, which 4 lines. And then you're ready to do the multiplication of each and then add them up or subtract them. So this would take more lines if I had done it carefully and properly. Compare your speeds. Well, jury's out because I didn't actually compare them. I was sloppy, but I'll say C is faster. Question mark? Try it. I think it's going to require more than 2 lines because just finding, or more than 7 lines, because just finding this would require 5 lines, right? 1, 2, 3, 4, I guess 4 lines. 1, 2, yeah, 4 lines. And then 5, 6. Maybe they're the same. Doesn't matter. Use the telescoping form because it's supposed to be faster, right? And that's why we introduced it. But you can rewrite this little guy in the appropriate number of steps if you feel like it, which I do not. So I'm not going to. Okay. Has a little note about polynomials and listing just their coefficients. But then you definitely have to include the 0 coefficient. And so in the background, when you're dealing with polynomials, although you're able to enter the x to the 4 and x to the 3 and whatever, usually it ignores that. And in the background, it just works with the coefficients. Which is kind of fun. How about the binary search? You heard of the binary search? Have you done any searching? Yeah. Hey, I got one head nod over there. So, what's the binary search?
You have like a list and then cut it in half. Things in there and then not cut it in half. Search the part, pick the fastest.
Exactly. On a sorted list. So what we're going to have are keys, and it's going to go through and search it. Now, this is not my strong suit, reading code like this, but I think it's kind of fun. So the binary search would look something like this. So this is in Sage Math, which is a language. But I mean, it looks like any other language. Yeah. And so we can define a binary search on R, J, K, and some value C that we're trying to look for. Now it looks to me like J is the lower key and K is the higher key. Whereas here they've defined them in the opposite direction. So that I found kind of confusing. But the context of how they've defined the binary search here kind of clarifies it, I think. So here I'm just going to say higher and lower question mark from down here. That was the only thing that this looks like they copy pasted from something else, and so they probably didn't check it. Having been on the other end of that, copied pasted something, oh, that'll work. No, it doesn't. Okay, so just like he told me, we're gonna initialize found to be false. We haven't found C yet. Okay. And so if J is less than or equal to K, which it should be, then the midpoint is the floor function, which if you have a decimal, it just drops it down to the lowest whole number. Okay. J plus K, which is what? It's going to be the distance between J and K, and then divide it by 2. Okay. Where K is the upper value and J is the lower value. Then we print a little message probing at position and whatever the midpoint is. So if the key at the midpoint is C, then you found your key, right? And so then the location of that C is the midpoint. That's a lucky draw, right? The thing you were looking for was at your first division, right? That never happens. But if it does, rare, then you can return found as true, and then you can print found in position and then the location. Okay? And you can return the location. Otherwise, if the midpoint that you found, because this is on a sorted list, and so if the midpoint that you found is greater than C, right, then in terms of a sorted list, then you would have to go below the midpoint to find your value, right? Because the thing you're looking for is less than what you found at the midpoint. Yeah? So then we adjust our binary search, and so now we chop the lower half in half, and we say, okay, from J, which is our starting position, to mid minus 1, because we already excluded mid, right? We said, well, it's not that, so, and it's less than that. So now I go to the next point here, mid minus 1, and I start looking for C again. If the midpoint is not, so if it's less than C, then my C is on the upper end of the half. So then I need to do the same thing for the upper end. Otherwise, we're going to print not found. So if we go through all this and we work through it and we don't find any, we don't find C, then we return not found. So if we have some S, I would call it an array S. Would you? Maybe. It's a sorted array, 1, 9, 13, 16, blah, 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 blah. So it's all sorted here. And so these are the values that we're going to be working with. Just want to make it a little bit bigger so we can look at it. Yeah. Okay. So this is the sorted list, and yes, that is the smallest or the largest value here. And the position is 0 indexed, so it starts at 0. Or sorry, not the position. The binary search is 0 indexed. And so you can find the length of S, which is, I think, 28 I got to. The length of S is 28, which means that if I'm going from 0 to 28 minus 1, right, if it's 0 indexed. And so that's where I get this 0 to the length of S minus 1. I'm looking for the value 30 in this array S. And so what the binary search does is the first thing it's going to do is find the midpoint, right? The initial midpoint, which is 27 plus 0 divided by 2, and then the floor function, right? Floor function on j plus k divided by 2. Mid is 0 plus 27 divided by 2, which is 13.5. But we want the floor of 13.5, which puts me at 13. And that's where it's probing at position 13. Where is that on here? Where is it? Where is it? Okay. Now, where did I land on this? The positions are 0 indexed? I feel like they are. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I did land on that. That's my initial mid. Then I'm going to check, is 50 equal to 30? No. 30 is less than 50, telling me that, okay, you can limit your search. Your next binary search can be limited to these guys. Oops. Right, I already excluded that this point is not it, right? And so then my next thing that I'm going to do is so the midpoint 50 is larger than C. So what we're going to do is we're going to do a binary search on this, which we'll call R, right? This subset, okay? The lower half from 0 to mid minus 1, right? Go down minus 1. Okay? And I'm still looking for C. So then I can find the cut off point there. And so I can go from 0 to 12. 0 plus 12 divided by 2 puts me at position 6, which means that I'm going to be at 0, 1, 2, 3, 4, 5, 6. I lost it when I changed my color. 0, 1, 2, 3, 4, 5, 6, 32. I have to say it out loud. So that's my new my new midpoint, which is still larger than 30. So then I would do the same thing again. What's going to happen? Now the midpoint looks like it's going to be 1, 2, 3. 1, 2, 3. The floor function, I feel like position 2, yeah. 13, which is less than 30. So then I limit to the upper half, and I eventually would find that it's at position, oh, where is it? Here. Found in position 4. Which is 0, 1, 2, 3, 4. Ding, ding. but you'd have to go through recursively and sort through. All right. Shouldn't say sort because it's already sorted. Search through. Okay. Sequences. I'm not going to spend a lot of time here, but there are a lot of sequences to talk about. And so there are things like the geometric growth sequence, or you've probably heard about the Fibonacci sequence, right? Which I might be wrong, but I think it models population growth in rabbits. You just need to start with one rabbit. Now you have 2 rabbits, and then you have 3 rabbits, and then you have 4 rabbits and 7, I think it is, 5, 8, something like that. Anyways, both of those are sequences or recursive. And so let's have a look here. So what we do is we define some sort of basis. Which we're going to be trying to peel back to. Okay, so B0, or often we call B0 B naught, right? So null, is 100. Now BK, so the kth B, is going to be 1.08 times BK minus 1, which is the previous B, right? For any K that's greater than or equal to 1. Okay, and so what we can do is if we just take a simple example like B3 and we break it down, then we're going to be doing the same thing that we were doing with 7 to the power of 5, right? That's really 7 times 7 to the power of 4, but that's really 7 times 7 to the power of, or 7 times 7 to the power of 3, right? So we're doing the same thing. We've got 1.08 times the previous B, but that's 1.08 times 1.08 times B1. B1 I can rewrite in terms of the basis, which is B0, which we know is 100. So now this looks like 1.08, okay, spoiler alert, to the power of K times B0, right? Looks like 1.08 to the power of K times B0. Right, K is 3, which is what we're getting to. Another sequence that we could look at is the Fibonacci sequence, which has 2 basis things, points. F0 is 1 and F1 is 1. And Fk is Fk minus 2 plus Fk minus 1. So it adds up the previous 2 Fs that you saw. Okay. So let's do that one on the side here. F to the power of, or F4, then, if you had to rewrite it, right, peeling back until you have F0 and F1, then this is going to be F4 minus 2, which is 2, plus F4 minus 1, which is 3. F2 I can rewrite as F2 minus 2, which is F0, that's good, plus F2 minus 1, which is F1, which is also good, because I know that these are both 1. Now moving on to F3, going to be a little bit more work here. move them over, plus F3. F3 minus 2 is F1, plus F3 minus 1 is F2. F1 is good. We know that's 1. So the only thing that we need to pick away at is F2. So this is going to be 1 plus 1 plus 1 plus F2, which is F0 plus F1. And both of those equal 1. 1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5. So this is how to find F5 recursively. That's fine. Just peeling back until we have nothing left. If we wanted to find it iteratively, we could also find F5 iteratively. Which is going in the opposite direction. I start with my basis, and then I build up from there, which means that I could say, okay, F0 is 1 and F1 is 1. Then I can pick up at F2. F2, by definition, has to be F0 plus F1, right? F2 is F0 plus F1. I'll write it across here, which is 2, right? 1 plus 1. Okay. What about F3? F3 must be F3 minus 2, which is F1 plus F2. But I just found F2. So now I'm snowballing it. And so F1 is 1, F2 is 2, so now I have 3. F4 is F4 minus 2 is 2, plus 2, 4 minus 1 is 3. Right, just the previous 2. 2 plus 3 is 5. I wrote F5. That would be so confusing later. F4. We could also find F4 iteratively. We didn't go to 5. Could go to F5. Why not? But I think you get the hang of it. So iteratively is when you start from the bottom and then you snowball your way out, right? So you're kind of building the onion back out. This can be a little bit faster, at least for mental math, right? And there's all this theory about which one is faster. In some cases, working iteratively will be faster. Sometimes working recursively will be faster, but that's not my job to tell you, because I don't know. I'm not a computer scientist. That's what they do. Order n and that kind of stuff. Ugh. Okay. Good. Oh yeah. I think it's the last thing I want to do. Yes, it is. So before, when we had that formula for BK, now I'm going to add something here. This should have B subscript K there, because otherwise it's way too confusing. So here we're proposing that a formula for the sequence BK, I'll specify BK, is 100 times 1.08 to the power of K, as long as K is greater than or equal to 0. We're going to prove it by induction. Okay. And we haven't done proofs of induction, so I'm just going to gloss over it because we don't really need it. But if K is equal to 0, so what we're going to do is we're going to build this thing up. Okay. Then BK, where K is 0, would be 100 times 1.08 to the power of 0. So that's fine. That's exactly what we were told it was. B0 was 100. Okay. Now, we're going to assume that the formula is true, which means that BK plus 1 must be 1.08 times the previous BK, right? Which is 100 times 1.08 to the power of K. And so now I have 100 times 1.08 times 1.08 to the power of K. All of a sudden I have 100 times 1.08 to the power of K plus 1, which matches exactly what we laid out. So because it behaves that for any K, like that for any K, right? We changed it to K plus 1 and it's still true. So then now we can say that it's true for any K plus 1. Yeah. Notice here that this is no longer in terms of a previous B subscript K or anything like that. When we see that, when we just have K in the formula as a number, then we call it a closed form expression. No B subscript K in the formula, just K is what it means. Okay. Because it no longer involves any recursion or summation. This is highlighted, but nah. No. There's a lot of summations, like the sum from K equals 1 to n of K would keep growing and growing and growing, but there are proofs out there that we could rewrite that as n times n plus 1 over 2, but we'll leave that for a later course. How's that for a cop-out? Okay, now we didn't do this one, but what I want to do is I'll put it at the end, and you're welcome to work on it now, but you might be a little sleepy. So what I want to do, because it's just going to be pretty tedious, what are we doing? By the recursive definition of binomial coefficients, then we know that 7 choose 2 can be rewritten as 6 choose 2 plus 6 choose 1. We want to continue expanding this until it's defined by the basis, which is either n choose 0 is 1 or n choose n is 1, right? And then you're going to check your work by using a factorial definition of n choose k. Okay? And so it's going to be quite tedious, and no, I don't want to do it up here. I'll go do it in my, well, I can do it here if you want, but I'll let you work on it, plug away at it, be nice and careful, and then check against the notes when I post them. Any questions? No, that's plenty. All right, no questions. Then we're gonna get to start chapter 9 on Friday. Finally, graphs, trees, in chapter 10. Here we go. All right. Until then.